Here. Okay, is everyone still able to hear me?
Yep, we can still hear you.
Okay, great. All right. So, all right, great. So today's lecture is going to be on field effect transistors. So we've completed the diode chapter now. We talked about metal semiconductor junctions. We talked about purely semiconductor junctions. And a lot of those, especially the metal semiconductor junction, is going to come into play when we talk about field effect transistors. So this is probably the most important module in this class. We're going to be covering the MOSFET, the metal oxide semiconductor field effect transistor. It's the second of the three major devices that's covered in this class. But a lot of the focus on this class really is on the MOSFET. There are different types of field effect transistors as well, including the MOSFET, the HEMT, and the JFETs. These devices they're used, but they're less often used than the MOSFET, which has really become pretty ubiquitous today. And so that's why we're going to focus on this particular device. As I mentioned before, some of the concepts that we talked about with metal semiconductor junctions in the previous chapter is going to come into play here. But a lot of it is going to be on some fundamentally new concepts. So that's why, it's important. We're going to spend a lot of today talking about the really fundamental concepts. We're going to talk about energy band diagrams. We're also going to talk about the physical model of what happens that causes a MOSFET to become inverted and allow conduction between the source and the drain regions. And later we're going to get into the more quantitative stuff like calculating values and things like that. So your focus today really is going to be on just getting a solid qualitative understanding. We are on the online lecture today, so please feel free to blurt out questions. That might actually be better than typing questions into the window, because I can't see that window while I'm discussing the slides. Sound good, everyone? Okay, I'll just assume that's a yes. All right, let's start with this. Why are metal oxide semiconductor field effect transistors? Why are they such a big deal right now? There's obviously many different important applications of MOSFETs. Probably the
Are you sharing your screen?
Oh, maybe I'm not showing my screen yet. Okay, thanks.
Yeah, we can't see your screen.
Okay, here we go. There we go. Now you all should be able to see my screen. Is everyone able to see my screen now?
Yes.
Great, great. So why are MOSFETs such a big deal? There's two important applications, and both of these applications, you could argue, has really transformed the way that we live compared to what technology was like, only like about 15, 20 years ago. The first aspect is digital switching, and the second is amplification. So the first application of a MOSFET is digital switching. So the current in a transistor can be switched on and off by changing the gate voltage, and we'll talk about why that's the case. The difference between a transistor and a switch on the wall, so imagine just a light switch on the wall. The light switch on the wall requires you to physically move the switch to the up and the down position. Now, imagine how quickly you could turn a light switch on and off. Maybe a few times a second, so 3 Hertz. So being able to switch something on and off is a central part of computation, because logic gates like inverters, AND gates, ALUs, like all the computational logic is built on the concept of a switch. Now, if your switch can only work at 3 Hertz, if you had a mechanical switch, the clock rate of your CPU would be 3 Hertz. MOSFETs are switches that are digital. They're electronically controlled. By applying a voltage on the gate, you can control current between the source and the drain. And an electronic transistor nowadays can operate at 3 gigahertz, so 3 times 10 to the 9th cycles per second. So it's obviously a much faster way of doing switching, and also we can make the transistors very, very small. Nowadays, the latest nodes that are under research by IBM and Intel right now is a 7 nanometer node. So 7 times 10 to the negative 9 meters. The gate is only a few atomic layers thick. By making the transistors very small, we can cram a lot of them onto an IC. All right, so this is an example of that. We look at this Intel Skylake i7 processor. So these just came out maybe 3 years ago or so. This device, a Core i7, has close to 2.1 billion MOSFETs on there, which is quite amazing. They're organized into 4 different cores. This is a quad-core system here. So it allows you to do parallel computation. Now, similarly, you have the NVIDIA GPU, which takes this idea and takes it 1 order of magnitude greater. There are 21 billion transistors on a typical NVIDIA GPU. Does anyone know what GPU stands for?
Graphics Processing Unit.
Graphics Processing Unit. Yep. So hey, everyone else, don't be shy. You know, David's been pulling the weight here. So please, everyone else, please feel free to chime in with your inputs as well. So graphics processing units have become very important just in the last 5 to 7 years because of their ability to perform deep learning. I'm sure some of you have heard the term machine learning and deep learning. So these types of computations require a large amount of matrix calculations. And it turns out GPUs are very good at that. And they also require parallelized computation, meaning that there's multiple computations going on at the same time. The traditional microprocessor only had 1 logic unit in it, 1 core. So this allowed you to do 1 computation at once. And nowadays, the NVIDIA GPUs have 5,120 cores, so you can do 5,000 calculations simultaneously. And that's one of the reasons why GPUs have become extremely popular in some of the deep learning type computations that are done mostly in the cloud nowadays. Like companies like Google and Facebook are using those kinds of methods to do facial recognition, natural language processing, and so forth. So this has to do with digital switching. The fact that we're able to make the transistors very, very small, and the transistor being the elemental unit of a digital logic gate, this allows us to do incredibly complex amounts of computation through the use of MOSFETs. The second group, which is why MOSFETs have become very important, is because they can also be used to amplify analog signals. And so some of you may recall from your undergraduate classes that there are, you can build several types of amplifiers, 3 very common types of amplifiers you can build: the common source, the common gate, the common drain. Those are amplifiers that can amplify an electronic signal. It can amplify a voltage signal. It can amplify a current signal. And that turns out to be very important because you can do these types of amplification using MOSFETs. Now, in the past, analog circuits often use the bipolar junction transistor to be able to amplify signals because they had some properties like gain and speed that were preferable over the MOSFET. But the bipolar, being able to make a bipolar junction transistor required a different process entirely. Whereas all the computational stuff, all the CPUs were being made in a CMOS process. The bipolar junction transistors had to be made in a separate bipolar process. Okay, so you'd have separate wireless radio chips made in a different process and separate microprocessor chips made in the CMOS process. One of the big things that happened in the late 90s to early 2000s was the ability to make amplifier chips out of the traditional MOSFET. Usually MOSFETs weren't as good as amplification as BJTs, so specifically it was difficult to get them to work at fast speeds in the 2.4 gigahertz range, which is required for cellular radio. It's required for Wi-Fi, those are Bluetooth, things like that. But sometime in the late 90s and early 2000s, there were companies that figured out how to make radios with MOSFETs. And so suddenly we had this ability to do radios, wireless radios, and microprocessors in the same process. And that's totally changed, changed the world in the last like 10 years or so. Let me back up for a second here. I'll get into that in a second. Why is amplification important for wireless? So I would like someone to, someone besides David. David, thank you for all your input. Why is amplification important for wireless communications?
I mean, I would imagine it would help if you're getting a weak signal or something like that.
Absolutely. So you're right on track. So imagine, you have your cell phone in your pocket, or your Wi-Fi radios that are on your router. All right, these things are picking up pretty weak signals that are coming from cell phone towers. Let's take the example of a cell phone. And the signals coming from there might be like, negative 80 dBm, even more, like negative 100 dBm or so. So you need you need fast amplifiers, and you need sensitive amplifiers to amplify that signal from the cell phone tower into something that your cell phone can read, right? And so the fundamental component of a wireless radio is an antenna and an amplifier. So you have to have both of those things. So once we figured out how to make amplifiers out of MOSFETs and have them operate at the speeds required for cellular radio, this enabled us to put radios into chips that also had microcontrollers in them. If you've ever heard of the concept of a system on a chip, it's a chip or multiple chips in the same package that have all the components that you need. It has a microprocessor, it may have some sensors, it may have some a wireless component for a wireless radio. And our ability to integrate all those in the same manufacturing process, in the same chip, greatly, it totally changed how we think about wireless. Now most of you know that there's wireless in everything. There's you have wireless Alexa, you have wireless Google Assistant, you have wireless cell phones, you have all your laptops are wireless. Nowadays they even have like the things like wireless toasters and wireless Instant Pot and wireless, everything is wireless nowadays. And one of the fundamental things behind that was the ability to for CMOS MOSFET devices to be able to do wireless communications. So I want to point out this thing on the right. Can everyone see my mouse? Yes or no?
Yes.
Okay, great, thank you. So this is an example of an extremely tiny integrated system. This is called the Michigan Micromode. This is some research that's done at the University of Michigan, Ann Arbor, just 45 minutes down the road. They're able to make, this is the side of a dime here. They're able to make an entire system, including sensors, including a microprocessor to acquire data from that sensor, and a wireless radio that can communicate up to a few meters away into something that's not much larger than a grain of rice. It's really quite amazing. And if you're thinking about what the future of electronics is, this is really it. There's this thought that we are going to have sensors everywhere. Wireless sensors that are sensing everything from pressure to water quality to like radiation and sound, structural things like bridges and things like that. There's going to be sensors everywhere. This term is sometimes referred to as the Internet of Things, IoT. And some people just call it the sensor revolution. There's many different names for it. But basically, this idea that if you can make your sensors, your computational components, and your wireless all in the same manufacturing process, and to make it all very, very small, these things become dirt cheap and they're deployable everywhere. One of the, there was a famous term that was coined by, I believe, someone at the University of California, Berkeley, which was called smart dust. And that was kind of coined the idea, probably in the early 2000s, that you would have these sensors and devices that were basically the size of dust particles that can do, various types of sensing applications. All right. So I mentioned that before MOSFETs, bipolar junction transistors were used, and even before that, the way that amplification was typically done was these things called vacuum tubes. And vacuum tubes were used in some of the amplifiers that are in the old school radios. They're still used in some of them. Some audio folks who really prefer that type of amplification as opposed to the transistor amplifiers that are available today. Those are, if you ever see one, they're quite huge. So they're not really apt towards a miniaturization. So the fact that the ability to do amplification in the MOSFET devices has really changed society. So any questions on this, on the importance of MOSFETs? All right, great. Moore's law we talked about before. I'll touch on it again now. One of the things that happened over the last 30 years was that we were able to make transistors smaller and smaller. And that's, in effect, what Moore's law is all about. 1971, Intel released one of its first microprocessors, the 4004. It had 2,300 transistors. Each transistor, the gate length was about 10 microns in size. So this was the size of the MOSFET. And these MOSFETs worked at 100 kilohertz clock speed, and the typical RAM in these devices was 640 bytes. And I mentioned this probably earlier in the semester too, but nowadays we're up to well over 1 billion transistors. I showed you on the previous slide. This is a processor from the 2000s, the Pentium 4. It had about 40 million transistors. We're up to 20 billion now. But by making the transistors smaller, it turns out that transistors actually work faster. And you can think about this in terms of transit time. When you have a smaller transistor, it takes less time for electrons to travel through the device because there's less distance to move. And you can also think about it in terms of capacitance. We're gonna talk about the gate capacitance of a MOS capacitor. So we'll get into that later. But basically, as you make the transistors smaller and smaller, it turns out they work faster, and you're able to cram more and more into an area. So that does two things. The higher clock speeds makes for faster computation. Higher clock rates translates into faster computation. Cramming more and more transistors into the same amount of space allows you to make more complex computation. As I mentioned, I showed you on the previous slide, these NVIDIA GPUs, by parallelizing, by having many transistors like operating in parallel, you can do parallel computation, really complex matrix calculations, which are suitable for graphics and gaming, and also for deep learning and scientific computation. So those are the two things that happened. And so Intel, over the course of 30 years, they just kept on making their transistors smaller and smaller. Gordon Moore, the founder of Intel, who this law is named after, predicted that the number of transistors on a wafer would double every 18 months. And he was pretty close. They ended up doubling every 24 months, which is a pretty remarkable prediction for something that lasted about 30 years or so. So over the last several decades, you can see the various lines of Intel microprocessors that have come out. And as soon as one processor came out, they were already working on the next generation. And that continues to this day. So Intel has their Skylake processors out right now. And they're currently working on, they're already working on the next generation, which is getting a lot more tougher now. Some of you have probably heard of articles that say we are currently at the end of Moore's law. And what that means is that Moore's law was based on the idea of shrinking transistors. at some point, it becomes very hard to shrink the transistors any further than they are right now. I didn't mention it here, but the Intel Skylake was using something like, I believe, 12 or 14 nanometer transistors. And that's already quite small. The next generation that they're looking at far out is a 7 nanometer node. 7 nanometer node, they're looking at 7 nanometer transistors. These are at almost at atomic scale. A nanometer, you're talking about like, 1 atomic layer thick. So these, 7 nanometers, so you're just talking about a few atomic layers. And it becomes very, very difficult to make transistors reproducibly at these particular size scales. So it takes more and more effort, many billions of dollars, to go from a 12 to 14 nanometer node down to a 7 to 10 nanometer node, right? And at some point, it becomes impossible because of various types of effects, quantum effects that start to happen when your devices are at atomic scale. So we'll touch a little bit on that in this module, but the main focus of this module is for you to understand the fundamental concepts about how a MOSFET device works. So when people say it's at the end of Moore's law, what they're referring to is the difficulty in miniaturizing transistors more than they already are right now. And that's one of the reasons why I'm sure some of you may have noticed that the transistor speeds are not increasing at the rate that they used to before. So I grew up in the 80s and 90s, and during the 90s, it seemed like every couple of years, the speed was doubling. The speed of the microprocessors, they were going from, first they went from several hundred megahertz to like 1 gigahertz, then 2 gigahertz, and 3 gigahertz. It went very quickly. And then you'll notice that over the last like 5 to 10 years or so, we're not able to go that much faster than 3 gigahertz. We're kind of stuck at that thing. And then part of that reflects the fact that we have a lot of difficulty in making the transistors smaller than they already are. All right, so what people are doing instead, what a lot of the companies are doing instead is, okay, we can't make the transistors any smaller, so we can't get faster clock speeds. Let's get better performance by parallelizing and having multiple cores. And that gets back to what I showed you on this previous slide. Intel's creating multi-core processors, and NVIDIA's doing many core GPU systems. All right, so it's trying to get more performance by parallelization. All right, any questions on Moore's law? Okay, great. So let's get into the MOSFET then. We'll talk about the structure of the MOSFETs with the IV characteristics in the 3 regions of operation, the cutoff, the triode, and saturation. And then we'll talk about the physical and energy band model of each of the modes of operation. There's many of them. Equilibrium, accumulation, depletion, inversion, triode, saturation. We'll touch on all of them. And then we'll get into some of the transient characteristics, like what determines the speed of a MOSFET. What limits the clock speed that it can operate at? So let's first talk about what the 2 types of devices. There's the NMOS device and the PMOS device. And the symbols for these are shown at the bottom here. All right, so here's how these typical devices work. You apply a gate voltage. You apply a voltage between the gate and the source. So just imagine for a second that the source is, Imagine for a second that the source is grounded, and then you apply a voltage. You apply a voltage on the gate, so you see this VGS here. Okay, and when you place a sufficiently large voltage on the gate, you allow current conduction between the drain and the source. So one of the things that's different about the MOSFET is that it's a 3-terminal device instead of a 2-terminal device. Now, in class I mentioned before that the MOSFET is a switch. So let's really talk about this thing as a switch. All right, a switch has, the two terminals of a switch. We're going to call them the drain and the source. All right, so imagine a light switch for a second. All right, you have, your electrical circuit is connected on one end of, let's say, connected let's do a regular switch. So let's say you have a voltage source, and then you have a light bulb. This is a terrible drawing of a light bulb, so just don't mind me. All right, so when you close the switch, sorry for that. When you close the switch, now you have, now your switch is on, and you conduct current this way, and that's what completes the circuit, and that's what turns your light bulb on. Now, in an NMOS device, these are the two contacts for the switches, the drain and the source. So the current is going to flow from the drain to the source. Okay? And the purpose of the gate is that it controls whether the switch is on or off. So when a VGS is applied, when you apply a gate voltage and that gate voltage is greater than the threshold, then you can imagine that there's current conduction between the drain and the source, like that. Okay, and if you remove that gate voltage, then this goes away. And there's no conduction between the drain and the source. Any questions so far on the NMOS device? Okay. So in addition to the gate voltage, you also have to apply a drain to source voltage as well. Because, like a switch, if you imagine a switch that's not connected to anything, well, that switch is really not going to do much, right? You have to have the switch connected to an external circuit to drive current through the switch. All right, so you still have to have, the drain to source still has to be connected to a circuit in order to drive current through there. All right, so in order to get a current ID, you need to have a gate to source voltage to turn the MOSFET on, and then you also have to apply a voltage here to get the current to go from drain to source. All right, a PMOS device looks similar to the NMOS, but it is you could think about it as the inverse of the NMOS device. So what you see is that the source is on top here and the drain is on the bottom. So in a PMOS device, the current flows from source to drain instead of from the drain to the source. And the voltage is applied between the source and the gate. All right, so instead of the gate voltage being higher than the source voltage, as is the case with NMOS devices, now the source voltage is greater than the gate voltage. All right, in order to turn the device on, your VSG has to be larger than a threshold. All right, for the NMOS device, it's the opposite. When you turn the device on, that allows current flow between the source and the drain, and the current flows from the source and the drain. You apply voltage between the source and the drain in order to drive current through. All right, so these essentially are electronically controlled switches. Both of these devices are. All right. Any questions so far? Everyone's with me? Okay. These are the IV characteristics of a MOSFET. We'll get into more of the details of this later. But I'll just, I want everyone to see this now. How many of you have seen this before? Let me, you can actually put something in the window now if you'd like. Just say a quick yes or no. You've seen the IV characteristics of the device before. Yeah. Okay. All right. Okay. We have a couple no's, and that's fine. Okay. So that's fine. So then it's helpful if we go over this. So in an NMOS device, there's the current that flows between the drain and the source, and then there's this that drain to source current is a function of the gate to source voltage and the drain to source voltage here. Okay, so notice that if we just have something as simple as a resistor, so let's say we just have a resistor like this. There's voltage is equal to the current times the resistance. This is a two-terminal device. You apply a voltage, you get a current based on whatever the resistance is. Since this is a three-terminal device, we actually have to apply two inputs to the system. We have to apply a VGS, and then we also have to apply a VDS. We have to apply both. And the current ID is a function of both. So that's why these curves here, you'll see a bunch of different lines here. Now, so the first line I'm going to draw, which is actually not on this graph, but let me just draw it. It's this red line down here. This red line represents VG, the gate to source voltage, equals 0 for an NMOS device. The gate to source voltage is 0. And when the gate to source voltage is 0, I mentioned this, that the transistor is off. So there's no current between the drain and the source. So that's what's being shown on the y-axis here. The y-axis is showing the drain to source current. So when you have a gate voltage of 0, the drain current is 0 like this. If you now apply a gate to source voltage, now your transistor turns on. Okay, if your gate to source voltage is greater than the threshold voltage, the device turns on. Now what happens is that now the device can conduct electricity. You can flow a current from by applying a voltage on the drain to source, you'll get a current flow. As you increase the drain to source voltage, VDS, the current goes up like this in the triode region, and when you get to the saturation region, the current flatlines like this. Okay, so what that means is that flatline means that even if you change VDS, the current doesn't change, which is kind of interesting. All right, so if you apply a voltage to something, and the current, regardless of whatever voltage you apply, it stays the same, what fundamental electrical component is that? So someone who's taken a circuits class before, it's a component that provides, it provides a fixed current regardless of what voltage is applied to it. Okay, people are too quiet. I think I need to call on people. Let's see. Someone who's taken electronics classes before. Dominic, you were in my electronics class before. So what type of electrical component is it when you have a fixed current regardless of voltage? Dominic, are you there? Okay, Dominic's saying I'm not sure. Well, okay. It's does anyone else want to try? Okay. Yeah, a current source. A current source is one of the components in electrical circuits where you have some kind of current I. So the current source gives a constant current regardless of what voltage is set across it. So In the saturation region, the MOSFET device can actually be used as a current source. And then when you do it, when you try to do amplification, it turns out current sources are very important. All right. So that's a function of the MOSFET. Now, if you increase the gate voltage, you'll get the same type of curve. It looks similar, except the currents are larger. And the reason for this is that you can think about by applying a larger gate voltage, you're opening up the channel more. You're making the channel more conductive, so you get larger currents when you apply voltages to it. All right, so again, the current increases during the triode region, and then once you get to the saturation region, the current flatlines like this, and so on for larger gate voltages. This graph, I just want to make sure everyone knows that this is this is for an NMOS device. We'll look at a PMOS device a little bit later. The triode region of operation, when the current is increasing with the drain voltage, this occurs when the drain voltage is less than VG minus VT, or VGS minus VT. And the saturation region happens when VD is greater than VGS minus VT. So at large drain voltages, you'll be in the saturation region. At small drain voltages, you'll be in the triode region. Okay. So we're going to talk about MOSFETs and digital circuits. The gate level stuff is covered in a digital logic class. Some of you have probably taken digital logic courses or computer architecture courses in your undergrad. If you look at the transistor level, so if you take a gate, this is a typical inverter gate. All right, an inverter gate converts a binary 0 to a binary 1, or a binary 1 to a binary 0. So this is the gate level. If you look inside the gate, then you'll see that a gate is composed of two transistors, a PMOS transistor and an NMOS transistor, and it has an input here and an output here. The way it works is that if you supply some kind of input voltage here, if I supply a high input voltage here, let's say 1 volt, and let's say that 1 volt is greater than the threshold voltage, then this NMOS device turns on. So you can have current conducted between the output and ground. So the output and ground are electrically connected to each other. And as a result, your output voltage is 0 volts. Okay. At the same time, I forgot to mention when you apply 1 volt to the input, let's say your VDD is also close to 1 volt. That means that the gate to source voltage here is small, so the PMOS device is off. So when you apply a high voltage at the input, the NMOS device is on, the PMOS device is off, and you basically get an output voltage of 0. If you do the opposite, if you apply a low input voltage, let's say you apply 0 volts at the input, then the NMOS device is going to be off, and the PMOS device is going to be on, and you're going to be electrically connected to VDD at the output. Right? So then your output voltage is going to be high. So this type of transistor level stuff is typically discussed in mixed signal, analog signal, or digital circuit design courses. In this course, we look at the physical level, so we're just going to be talking about the material properties of the diode. We're going to look at the physical structure of it, and we're going to basically calculate some of the essential operating characteristics that are used by the circuit designers when they do their transistor level designs. Okay, so electronics design is very hierarchical this way. You know, the physical, the device engineers and the process engineers work at this level, the circuit design guys work at this level, and then the digital logic and the computer architecture guys work at this level. Massive team of engineers working on systems like this. All right, so here's how a MOSFET controls current. I talked about this concept of electronic switching, so now I'm going to get into the details of it. So a MOSFET behaves as an electronic switch. I mentioned before that the gate voltage, it modulates whether the channel is on, whether the transistor is on or off. I'll say that again. The gate voltage determines whether the transistor is on or off. If the transistor is on, then you get conduction between the source and drain. And if it's off, you don't get conduction between the source and drain. All right. The way that the MOSFET does this is through a field effect. By applying a field to the gate region, you can actually switch a material from P-type to N-type and turn the transistor on. So let me explain what I mean by that. So let's say we have N-type material, P-type material, and an N-type material, like this. Okay, this is what a transistor actually looks like when it's off. This is an NMOS example of an NMOS device. So the source is an N-type material. The drain is an N-type material. Under the gate region of the transistor, it's a P-type substrate. All right. So let me just say this is an NMOS transistor. Okay. All right. Now, can someone tell me if we were to put a voltage between here? If we were to connect this to a circuit, would we get current flow? Would we get any current flow? So anyone, please, anyone's welcome to answer. Including David, if you'd like.
There's some responses in the chat.
Oh, okay. You know, I request if you can, you know, since I'm going to be looking at the slides, just feel free to speak up in the conference. Just unmute yourself and speak up. Okay. Yeah, it won't conduct current. And the reason it won't conduct current is because you have two p-n junctions. Okay, we talked about p-n junction in the last chapter. You have a p-n junction here, a p-n junction here. The equivalent circuit for that looks like this. Now, what is this current equivalent circuit showing? Okay, if you look at the N-type semiconductor, we know that the N-type semiconductor behaves as a resistor. That was chapter 3. We know that from last chapter, chapter 5, we know that wherever there's an interface between an P and an N-type material, that is a diode, and that's denoted by this diode symbol. All right, so in the P-type material, you have a resistance here, then you have another diode here, and then you have another resistor here as you go through the N-type material. Now, one of the things that we learned in last module is that diodes only conduct current in one direction. So this diode only conducts current in this direction, and then this diode only conducts current in this direction. All right, so if you connect this to a circuit, it's never going to allow current flow. It's never going to allow current flow because one of these diodes is always going to be reverse biased. One of these diodes is always going to be off because these two diodes are pointed in the opposite direction. Right? Diodes only conduct current in the forward direction. So as a result, this transistor, you cannot get any current flow going from the source to the drain. When the transistor is on, the way that we turn the transistor on is to actually, just mentioned, this is an NPN junction. Back-to-back diodes, no current can flow. We turn the transistor on, this is called inversion. We change the middle section, the gate region, we change it from a P-type to an N-type. Now what do we have? We have an N-type material, another N-type material, and another N-type material. There's no PN junction here. So as a result, this just looks like three resistors like this. All right? If you just have three resistors, of course, you can have current flow between the source and the drain. It just acts like a resistor. All right. So the magic of a field effect transistor, the key concept is how can we change this P-type material to an N-type material? How do we invert it from a P-type to N-type? All right. Well, what are the ways that you all know now to invert, to change a material from P-type to N-type? How can we do that?
Doping is one way.
Okay, doping is one way. Yep. Llama also says doping. Great. And I see Dominic is also typing here. Just wait for him.
Can you do carrier injection?
Yeah, you could do carrier injection as well. Absolutely. So carrier injection requires that you have carriers coming in from another source, and that expends current. So that would take up power, and I think that's one of the reasons why it's not done. And then you'd also have to worry about where those carriers are going. Now, doping is a way that we can invert a material, sure, but how long does it take to do doping? It takes a doping process typically takes a few hours. So if we wanted to switch our transistor on and off quickly, then doping is not a good option. We want to be able to switch the material from P-type to N-type within nanoseconds, if possible. So that is really what the magic of the MOSFET is all about, is being able to do what's called inversion, switching a material from P-type and an N-type. And the way the MOSFET does it is through a field effect, meaning by applying a voltage to the gate, we can switch the material from P-type to N-type. So that's what we're going to be talking about today. How does that process work? All right. So this is the structure and a physical interpretation of an NMOS device. We'll go through it one step at a time. So we start with the source and the drain region. So we start off with a P-type substrate, okay? So this is a P-type semiconductor. It's called a substrate because when you're manufacturing the material that you start off with when you're manufacturing something, they often refer to that as a substrate. And that's why we say it's a P substrate instead of a P-type semiconductor. But essentially it's a P-type material, which has low doping. All right? And first we can create the source and drain regions by doping it. All right? So and then you can add metal contacts to those as well. So now we have an N+ region within the P-type substrate that we formed by diffusion. So it's localized diffusion, localized doping. So now we have this N+ material here. The drain is also an N+ material. All right, and then in order to make an electrical contact to it, we have a piece of metal here. We deposit some metal on top of the source so that we can attach our wire to it. This is what's called a bond pad. If we want to make an electrical connection to the NMOS device. If you remember from last chapter, these are tunneling type contacts. So you have a metal semiconductor junction right here. All right, metal semiconductor junction can behave as a diode, or it can behave as an ohmic contact. If you have a really highly doped semiconductor next to the metal, then it forms what's called a tunneling type contact, and it's always ohmic, or very ohmic-like. So this forms an ohmic contact here. And then below here, we have an N+ region, and then we have the P-type substrate underneath. So there's a depletion region. There's a depletion region that forms here. And then you actually have a diode between the source and the substrate. Similarly, here you have a depletion region here as well that forms. Okay. Now, the next part of the NMOS device is the gate. So the gate goes right in the middle. All right, so from the last diagram, we're going to try to create a channel between the source and the drain. All right, this is P-type, and we want to switch that material from P-type to N-type and form a conductive channel between the source and the drain. So the way the gate structure looks like, the first thing is there's an oxide layer here. This is an insulating layer, okay? So it does not allow current to conduct through there. Unlike the metal is being used to make a conductive contact into the N+ material. Here we're specifically using an insulator, an insulating dielectric material. The next part of it is a metal on top of that. This is drawn in orange. It can either be a metal or it can be a conductive type of silicon that's called polysilicon. The highly doped polysilicon is conductive. And then you have your electrical contacts here on top of that. So this is what the structure looks like. And by applying a voltage to the gate, we can actually change this region here just underneath the gate. We can switch that from P-type to N-type. And we'll look at that on the next slide. All right, so this is what happens at inversion. So let's say we have our device like this. We have the source, the gate, and the drain here. The first thing we're doing here is we're taking a gate voltage. We're applying a gate voltage to here. Right. So let's say we take a voltage source, or a voltage source applied between the gate and the source. All right, and we choose a voltage so that the gate to source voltage, the voltage between the gate and the source, is greater than the threshold voltage. The VT here is the threshold voltage. Okay, and the purpose of this slide is just to qualitatively understand what happens at inversion. How do we invert this material from P-type to N-type? So when you apply a voltage there on the gate, you end up building up positive charges on the gate, and you'll also end up building up negative charges on the other side. One point that I want to make here is that you can think about the substrate as being grounded. All right, so when we apply a gate to source voltage, the source, for the purposes of this slide, just think about the source being grounded as well. So when we're applying a gate to source voltage, it's kind of like we're applying a voltage between the gate and the substrate. All right, and I'm putting it this way so it's easier for you to understand. Now, if you think about capacitors, what are capacitors? Capacitor is a metal. Okay, so you have a metal here. This is polysilicon or a metal. And then you have an insulator underneath that. And then you have another metal underneath that. So what we have here looks kind of like a capacitor. So they sometimes refer to this portion as an MOS capacitor. Metal, the orange, oxide, the green, and S, the semiconductor. MOS stands for metal oxide semiconductor. So this forms an MOS capacitor here. Capacitors, as you know, it builds up, if you put a voltage across the capacitor, so if you put a voltage between the gate and the substrate, you're going to end up building up positive charge on one side and negative charge on the other side. But let's look at what happens. Let's say that you've built up positive charges on the gate, and let's see where the negative charges come from. Now, the unique thing, a traditional capacitor is metal, dielectric, and metal. So you have metal on both sides. But here you have a metal, oxide, and semiconductor. A semiconductor has two types of carriers in it, so something very unique happens. So you build up this charge on the gate, and as you know, there's going to be an electric field. The electric field points from high potential to low potential. You have a positive potential on the gate, and your substrate is at ground. So you have electric field lines pointing down everywhere. So it's not just in the middle here. The electric field lines are actually pointed down everywhere like this. You have this positive charge buildup on the gate and this electric field pointing down. Now, what happens in a semiconductor is interesting. In a semiconductor, you have two types of carriers. You have electrons, and then you have holes. All right, can someone in the class tell me, what are the holes going to do if there's an electric field here?
They're going to move with the electric field away from there.
They're going to move away, right? Good. So you have holes here, and they move away from the gate. This process is called depletion. I'll jot that down there. So that's the first process that happens. The holes move away from the gate. What are the electrons going to do?
They're going to migrate to the gate.
Electrons are going to migrate to the gate. That's correct. So that's the second step. The electrons are migrating to the gates. This is the second thing that happens. All right, when you apply small voltages, this depletion effect starts to happen because you have tons of holes. A p-type material has a lot of holes, very few electrons. So even if you apply a small gate voltage, this depletion effect starts to happen right away. All right. The second effect, pulling in electrons. Remember, there aren't that many electrons because this is a p-type material. The second effect is called inversion, and it only happens at larger gate voltages. So let's write down inversion here. So the inversion process happens at larger gate voltages, specifically meaning when the gate voltage is greater than the threshold voltage. So these combine, the two effects, it creates, the depletion region, first of all. We'll get into that in a second. But the most importantly, it creates an inversion region. So when you have a whole bunch of electrons that are pulled in near the gate like this, just underneath the green region, you have a whole bunch of electrons that are collected there. And if you have a semiconductor that has a lot of electrons and very few holes, that is an N-type semiconductor. Right? That's a critical, very important point. We started off with a P-type material. We drove the holes away, we pulled in electrons, and now effectively we've switched it from a P-type material to an N-type material just by adding a voltage. And this effect happens within nanoseconds, even faster. It happens within, in some cases, it can, depending on what your gate voltage, gate thicknesses are, it can happen much faster than that. So now that we've created an N-type material underneath the gate, now guess what? Now current can flow from the source to the drain. We've turned our device on, right? So now it looks very much like kind of like an MOS capacitor with positive charges built up on one side of the dielectric, negative charges built up on the other side of the dielectric. But it turns out these negative charges that built up are actually electrons in the P-type substrate, and that creates a conductive channel just underneath the gate. And now you can conduct electricity between the source and the drain. Any questions there? Okay, great. So in order for this to happen, the VGS has to be greater than the threshold. All right, now let's look at the triode region. So now we've figured out that we can turn the device on, which is great. We can create a conductive channel, but now that conductive channel has to be connected to an external circuit. In other words, you have to apply some kind of drain voltage to the system as well. You apply VGS and you also apply a drain voltage, VD. And so in this slide, what we are assuming is that the drain to source voltage is fairly small. Okay, let me just draw the circuit diagram here just to remind everyone. The circuit diagram looks like this. We are applying a VGS here. Let's say the source is grounded. This is the gate. This is the drain. This is the source. Source is grounded. We're applying a VGS here between the gate and the source. And then we're also applying a VDS here between the drain and the source. All right? And so current is actually going to flow from the drain to the source when we apply a drain to source voltage. Okay, and the key thing is we are in the triode region, which means the drain to source voltage being applied here is quite small. It's less than VGS minus VT. All right. So we're applying this VDS here. That means the current is going to flow from here to here. The current flows like this. So you have a current I, and that current flows through here, takes a left turn here. It's flowing through here, through here, through here, through here, and then it's coming up like this. So it's flowing through between the source and the drain regions through the inversion channel that we've created. All right. Now I'm just going to erase some of the stuff underneath here so you can see. Okay. So the question is, why why does the channel look kind of thinner like this? The way that, what I mean by thinner, I've drawn it as physically being thinner, but what I'm trying to convey here is that the channel is actually less conductive on this side than it is on this side. So this is a tricky question. But bonus points to anyone who can figure it out.
Do electrons recombine as they travel through the P substrate?
That is an excellent probability. That's not the reason why this happens, but recombination through the N channel, that's a really interesting thought. I think what would probably happen is that as the electrons are traveling through here, since this is an N-type material and there's very few holes there, there's less chance at recombination. Let's see if anyone. Okay, there's ohmic behavior. Oh, that's also a thought, like you're talking about like this junction here, if there's any kind of interfacial behavior happening there. No, not quite it. This is a tricky question, so I don't expect you all to just be able to figure this out. But we'll talk about it in the next 2 slides, okay? And then I hope it'll make sense. The short answer is that the channel voltage varies as you go from drain to source, and as a result, the amount of voltage between the gate and the channel actually changes as you go from right to left, and that changes the conductivity of the channel. So that's the short answer. I'll give you a longer answer now, explaining from first principles. If you have a resistor like this, let's say this is one gigantic resistor. Okay. Some of you know this already, some of you don't, is that if you place a voltage across a resistor, you all know that you get current. That current is V equals IR. So that's the Ohm's law. But what you may not know or may not remember is that if you were to measure the voltage inside the resistor, if you were to somehow have like a multimeter and then you could probe the resistances at different places along the length of the resistor, what you'll find is that the voltage drops linearly as you go across the resistor. This is assuming that the resistor has a constant cross-section. That's a subtle point, but the most important thing to remember here is that the voltage drops as you go from here to here. It's not like the voltage, like, you start off at 10 volts here and then nothing changes, and then suddenly the voltage drops at the end of the resistor. No, that's not what happens. The voltage drops gradually as you go across the resistor, right? That's what's shown here on this slide. This is showing the position, the x-axis. You can think about this as the x-axis. The y-axis is the voltage. The voltage is going from 10 volts to 0 linearly as you're going across the length of the resistor. So what we have to do is we have to think about the MOSFET, the channel, the inversion channel. We have to think about that inversion channel as being a resistor. So within the NMOS channel, this section here that I'm highlighting with my mouse is a resistor. Current is flowing from here to here. It's going down on this side, it's flowing to the left here, and then back up this way. So as it's going through the channel, most of the voltage drop happens across here. So let's say we put 10 volts on here. So this side of the junction would be 10 volts. This side of the channel, sorry, would be 10 volts. And this side of the channel would be close to 0 volts. The voltage would decrease linearly as we're going from this side of the channel to this side. All right, so that's what's denoted as the channel voltage VD. It hits a maximum of VD. It's a channel voltage VC, I'm sorry. Channel voltage VC. It hits a maximum of VD, whatever drain voltage was applied to the system on the right side, and then it decays down to 0 linearly on the on the left side. So what does that mean in terms of the channel? Well, if we start with the left side, so what we're concerned with here is VGC, which is the gate to channel voltage. So this is equal to the gate voltage VG minus the channel voltage VCH. Okay, we can also call this CH. So on the left side, keep in mind that the voltage on the gate side, the metal, this is metal, so the voltage is really the same everywhere. There's no current flowing through here, so the voltage is the same everywhere on top like this. So the gate voltage is similar. The channel voltage is what's changing. So that's what causes VGC to change. On the left side, we have a gate voltage, but then we have a large, we have, let me fix this. Give it just a second here. I have a little typo in the notes. This should be lower channel voltage, larger VGC, larger electric field, and more inversion. I forgot to edit that. So on the left side, the channel voltage is low, so VGC is going to be large. And when you have a large voltage across a capacitor, that means more charge across the capacitor. Q is equal to CV. In a capacitor, the charge is equal to C times the voltage. So this is essentially a capacitor here. On the left side of the capacitor, you have a larger voltage drop. So this would be the gate to channel voltage, V. And so this is large, so then the Q is also large. That means you have a lot of negative charge in the inversion channel, so it's more conductive. On the right side, it's the opposite. So your channel voltage is larger, as I talked about here. Channel voltage is larger on this side. So your VGC, the gate minus the channel voltage, is lower. So you have a lower electric field there, lower amount of charge buildup, and so a less conductive channel. You have less inversion there. Okay, does that make sense? Because now's a good point to answer any questions you might have. Because from here on out, we're going to start to derive some of the equations. That's the next goal. Okay, so I'll take that as no questions. Oh, let me check the chat real quick. All right. Send me a message real quick. Tell me if you're with me or not. Let me know if you're with me or not. Let's check on that. All right. So this is why the right side of the channel is actually less inverted than the left side of the channel. All right. So another term that's used is that the channel starts to become pinched on the right side. And that's why I've actually drawn it this way, something that's with varying thickness. It's not quite the thickness, the dimension that's varying that much. It's really the amount of charge that you have, excuse me, in that region. Okay. So if we continue this, if we make VDS very large, there's going to be more current flowing through here. And so if we increase VD, then you're going to even have a larger voltage on the drain side, and even more difference between the voltage on the right side of the channel versus the left side of the channel. At some point, if the channel voltage gets too large, and the way we define that is when the drain to source voltage is greater than VGS minus VT. So this is your VGS here. Subtract out VT from that. If the drain voltage is larger than VGS minus VT, you get this effect, which is what's called a pinched off channel. Okay, so this pinch off effect becomes so pronounced that this side of the channel really has, you can think about it as being like very non-conductive. Few carriers in that region. All right, so it's not that this channel is cut off completely. Right, you still get current here. All right, so there still is a thin channel there, but a key point is that this is what's called the saturation region, and what happens is that if you increase the drain to source voltage once you're in the saturation region, if you increase the VDS, your ID doesn't change significantly because of the saturation effect. Questions? Okay, good. All right. So as a result, in the saturation region, if you were to increase this VDS further, once you're in the saturation region, the current doesn't change much. Okay, this physical phenomena of pinch off is actually limiting the amount of current that you can have in the system. All right, so the left side of the channel is highly inverted. The right side of the channel is just at the edge of not being inverted. Okay, so now we're going to look at the IV characteristics of the two modes used in MOSFETs, the triode region and the saturation region. So we're going to start the process by deriving the transistor current. So the way that we start about that is that we look at this basic equations of conductivity. We know Ohm's law and we know conductivity. We looked at conductivity in Module 3. We know that sigma is equal to mu, the mobility, times the volumetric charge density, which is coulombs per centimeter cubed. And if you remember, this is then equal to Q, all right. Is equal to mu n times Q times N plus mu P times Q times P in a semiconductor. This is for a semiconductor. All right, so what did this look like in a semiconductor? This is the mobility of electrons. This is the charge of an electron, and then this was the concentration of electrons. So the units, the units for this was 1 over centimeter cubed. The units was for coulombs, and this was centimeter squared per volt second. Okay, I'm writing kind of small there. Hope you get the idea. This bigger. There you go. All right, so this is the equation for conductivity, and on the right side is an equation for current. So current I is equal to V times the conductivity. So this is just coming from V equals IR. You know, V equals IR, R is a resistance, and I equals V times sigma. The sigma is the conductance. I said conductivity before, I meant conductance. So this is equal to V is equal to mu times Q. All right, so let's apply that to derive the current in the triode region. All right, again, where'd my mouse go? There we go. Okay, gotta load it up again. Give me a second. All right, so now we're going to derive the current. We know that there's this, these are the mobile electrons that have, aggregated near the gate region. This is the x coordinate. We know that the concentration of electrons is higher on this side and lower on this side. So this is the voltage, the channel voltage again. So we're going to focus on this aspect here. How much charge do we have in the channel? So the amount of charge we have, Qn, is a function of x. We have a lot of charge at x equals 0, less charge at x equals L, which is the length of the channel. All right. So Q, if you recall, the way that we can find charge is that we use this fundamental relationship Q equals CV. This is, the basic relationship for a capacitor. Q is equal to C times V. And this is a capacitor that we have here. So this is the dielectric, and then we have metal on top, and then the mobile carriers on the bottom. So we can just use that equation. Qn of x is equal to C, the capacitance, times the voltage across the gate. Now, this voltage is not just the gate to channel, it's not just VGC. No. Because this is a semiconductor and not just a basic metal capacitor, we have to take into account the threshold voltage, and we're also looking at how the voltage varies as you grow across the length of the channel. So this is the gate voltage. The gate voltage. This is the threshold voltage here. I'm not going to bother copying that down. And this V of x, this is the channel voltage. All right. So this is the amount of charge that you have going across the channel. Is you can see here that the channel voltage, we know that increases as you go from left to right. So as a result, the amount of charge that you have is actually going to decrease as you go from left to right. So there's going to be less charge on the right side. So if we just do a quick derivation, here's what it looks like. You start off with Ohm's law. ID is equal to the conductance times voltage. All right, and this conductivity becomes mu times Q. All right, so we started with Ohm's law, we come to this equation, and this is where we start using a little bit of calculus to make this work. So this is the differential form of the current equation. What we're doing here is essentially we are, where's the other graphic there? There we go. Yeah. What we're doing is we're taking this channel region and we're splitting it up into small pieces like this. Okay. We're splitting up this long channel here into small pieces, and each piece has a length dx. All right, you can already see that when you start using things like dx, that means you're going to do some kind of integration later, which we are. So we're first putting it in a differential form. So id times dx. All right, dx is the differential distance here along the length of the channel, is equal to mu n times w times qn times dv dx. So where is this coming from? Well, it's just coming from Ohm's law here. you can see that the mu becomes mu n. And the reason for that is because this is an n-type channel. So we have mainly electrons that are responsible for current conduction. So therefore, we just make this mu n. Then we have the width, W. Now the width is like this. So if you imagine that the transistor is actually a three-dimensional object, you know, the source looks like this, the drain looks like this, and the gate is in the middle, right? So this parameter here is the width of the transistor. All right. I haven't drawn that in the cross-sectional diagram because it gets a little confusing. This is the length of the transistor, and then what I showed you there is the width. Okay, so this is the Q sub n is the charge density, and the charge density multiplied by the width gives you the total amount of volumetric charge density times dVx. All right, so we turn this into a differential form by making this id times dx, and we make this v into dVx. All right, now that we have this differential equation is telling us the current and the voltage, the current and the voltage drop in each one of these small pieces of the resistor. So now we integrate both sides, and we are going to integrate from the left side of the channel here, where my mouse is, to the right side of the channel. Okay, because this dx, this differential component, is in the x direction. So we want to integrate over a range of x from x equals 0 to x equals L in order to figure out the complete relationship between current and voltage. Right, so we integrate the left side of the equation and we integrate the right side of the equation. On the left side of the equation, notice the left side of the equation is id times dx. All right, dx is our variable of integration. So we have to integrate dx from the left side of the channel to the right side of the channel. So the left side of the channel, the variable x, which is our variable of integration, x is equal to 0 on the left side, and then x is equal to L on the right side of the channel. So that's why we're integrating from x equals 0 to x equals L. Now on the right side of the equation, we are still integrating across the entire channel, from all the way from the left side to the right side. But we have a different variable here. The variable here is dVx. So this is the channel voltage. The channel voltage. All right. So something clever that you can do here is that your limits of integration, you're going from the left side of the channel to the right side of the channel. How does our variable of integration change as we go from one side to the other? The left side of the channel, the voltage there is 0. And on the right side of the channel, the voltage there is VDS, which are the drain to source voltage that you applied. All right, so that's why, you know, you're integrating both sides of the equation, but you just have two different variables on both sides, so they're going to have different limits. This is going from x equals 0 to L. This is going from v equals 0 to VDS. All right, so this is the interesting mathematical part, and then from here it's just straight up a simplification. We substitute q sub n here that we had from our 2 slides earlier, where we derived the q sub n, the amount of charge in the channel, and that's equal to Vg minus Vt minus Vx times Ci. So that's where these new terms come from. Right, and we're integrating from 0 to VDS. So if you just if you just integrate this equation here, this is Vg is a constant, Vt is a constant, and you have this Vx here. And if you do the integral of that, you end up coming up with this equation here, which is the current in the triode region. So this is ID is equal to mu n times Ci times W over L. This is the width of the transistor. This is the length of the transistor. Ci is Ci is the unit capacitance and the units for this is coulombs per centimeter squared. And the mobility, you know, this is the electron mobility, unit capacitance, W over L. This is the geometric parameter, Vg minus Vt times Vd. This term is linear because it's if you increase Vd, it's multiplied by Vd to the first power. The second term is a quadratic term, which is Vd squared divided by 2. All right. So the current in the triode region follows a fairly complex pattern in that it has a linear term and a quadratic term in it. So one simplification that you can make, though, is that at small levels of Vd, this term actually drops out. The reason for that is just this basic mathematical relationship that you may or may not remember. Let's say this is x and this is f of x. So let's say f of x is equal to x, like this. So this is a linear function, f of x equals x. Now let's say you have a square function. The square function looks parabolic like this. So this is f of x equals x squared. So what you notice is that at large values of x, the parabolic function is dominant, but at low values of x, at small values of x, the quadratic function actually becomes negligible. So we're talking about right here, where the quadratic term has become negligible compared to the linear term. So that's why you can ignore the quadratic term at low values of VDS. When that happens, then the triode equation becomes just a linear equation. I is equal to some constant times V. So it behaves very much like a resistor. Because remember this I equals some conductance times V. Right? So the conductance is equal to this whole thing right here. So what we're trying to say here, that the equation for the current versus voltage relationship in a MOSFET is linear when you're at low values of drain voltage. And so it behaves very much like a resistor. And in fact, we can derive the resistance. If this is the conductance 1 over, the conductance is 1 over the resistance, and that's what's basically being shown here. Right, so the conductance is equal to di over dv, and this is equal to mu n times w over L, Ci, Vg minus Vt. So you have a resistor that varies with the gate voltage. Increase the gate voltage, you reduce the resistance. So if any of you have dealt with potentiometers before, then you'll know that this is an electronic potentiometer. You could think about it that way. By controlling the gate voltage, you can control the resistance. All right. So let's talk about the current in the saturation region now. So in the saturation region, this occurs when VDS is greater than VGS minus VT. Just to remind everyone, this is the region that we're talking about here. So the saturation region is out here. Notice the triode region, the one that I just talked about. For small values of VD, it was linear. At larger values of VD, then it becomes more parabolic. That's when this VD squared term is kicking in. At small values of VD, these look like linear functions. But now we're talking about the saturation region, when VD is greater than Vg minus Vt. And this is where you see mainly flat current profiles. Let's just jump ahead here. Okay. Okay, back to here. So saturation occurs when VDS is greater than VGS minus VT. So the onset of saturation occurs at VDS equals VGS minus VT, and this is defined as the saturation voltage. So if we plug VD-sat into this equation, we get this formula here. So what we're drawing here essentially, this is VD, this is I sub D. So the triode region looks like this, and then it starts to kind of curl over like this, and then the saturation region begins here. So this is saturation, and this is triode. So ID sat is this thing right here. ID sat. It's the current at which saturation begins. And VD sat is right here. VD sat. The voltage at which saturation begins. That VD sat is equal to VGS minus VT for an NMOS device. All right, so this equation is just coming from the triode equation. All right, same equation as before, except we applied, we said that VD is equal to VG minus VT. And what you notice from here is that this becomes a function of VG minus VT squared. Okay, so the current modulates as a square function of the gate voltage. And this is one of the reasons why MOSFETs can actually be used as mixers. That's a whole different story, but this square function turns out to be very important for that. This is a summary of, I think we'll end with this here. What time are we at? We're at about 4:10. Okay. So just to quickly summarize, we can start with this next time because it'll be a good way of getting into this. But we'll just mention real quick that these are the NMOS device characteristics. I showed you these curves already. This is an enhancement mode NMOS device. The PMOS device looks the opposite. Okay, so instead of a P-type substrate, you have an N-type substrate. Your source and drain regions, instead of being N-type, they're P-type. And the conductive channel that's going to form between the source and drain regions are also P-type. So this is, the inverse, the mirror image, if you will, of the NMOS device. And so the current profiles are also the mirror image. They're reflected across the origin. You apply a negative gate to source voltage, and then your currents are negative because they're flowing from the source to the drain instead of from the drain to the source. But you can see that the shape of the current lines are pretty much identical. They're just inverted across the origin. So what I'd like you all to do at home is I would like you all to do this problem. Let's say you have an N-channel MOSFET with these parameters. Calculate the drain current when you have the gate voltage is this and the drain voltage is this. Calculate this under these conditions. What region of operation are you at here, and what region of operation are you at here? The answers are actually already given in the slides, and what I'd like you to do is make sure that you can go through and do this problem on your own before class next time so that you can feel comfortable as we move on through the rest of the material. The other thing I'd like you to do is think about these discussion questions, which I half answered right now, but I really want you to think about it. If you want to test your understanding of MOSFETs, then the best way to do it is to take the concepts that we learned for the NMOS device and see if you can apply them to the PMOS device. Meaning draw out the diagrams. Which direction are the electric field lines pointed? Which directions are the current flowing? Which carriers are moving in what directions, and so forth. Do that as an exercise at home, and it will make you stronger in this area. And then review this slide as well. We'll start with this slide next time, and then next time in class we'll get into all the energy band diagrams and such that describe the operation of the MOSFET. So let's see. We'll keep the ink annotations. All right. So any questions? Any questions before we end today's class? Lama is typing. Okay. Well, thank you all for being here. Monday's class next week and Wednesday's class next week will also be done online because I will be out of town, and so you all can just log in just as you did before through Canvas. And if you have any questions between now and then, please let me know. Do the problems at home and expect that you will get some kind of response from me about your outlines in the next few days. If you don't, please let me know and remind me. But I expect to have them by Friday or Saturday or so. All right. Okay. Thanks everyone for your attention. I'll see you all next time. Okay, I'll stop the recordings here.